Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. We're Science for the Public, and this is the Public Science Lecture Series. And tonight we are working on an astronomy topic again, which is suitable for here. One of the most interesting puzzles for modern astronomers is the formation and dynamics of galaxies. There's an awful lot that is still unknown, but the technological advances in our time make the prospect of understanding galaxies much more promising. We are very fortunate to have as our guest tonight an astronomer who's working with the most advanced techniques and equipment available today, and it's a very exciting time to be doing this work. She'll explain why the sheer complexity of galaxies demands the most sophisticated means and brains to explain their formation and dynamics. Elena is presently a Keck Fellow at the Harvard Center for Astrophysics, and in 2012, she'll be joining the faculty of the Astronomy Department at the University of Wisconsin-Madison. Dr. Dania received her doctorate from the University of Milan in Italy, where her research was concerned with dark matter at the center of galaxies. During her academic training, she was awarded a number of honors, and we'll try to list some of those on our website. After she received her doctorate, she was a Marie Curie Fellow at the University of Zurich and a research fellow at the observatory in Munich. Now at Harvard Center for Astrophysics, she's focusing on the dynamics and the evolution of galaxies. Dr. Dania has published very widely in academic literature, and she has also made an effort in her young career to communicate the mysteries of galaxies to the general public. This effort to translate scientific information to non-specialists is especially important today, as you all realize, and organizations like Science for the Public really applaud that work. We've inserted links to some of Dr. Dania's articles for non-specialists on the website, on our website, her page, and we encourage people definitely to take a look. And at this point, we would like to welcome Dr. Dania, who it's a great pleasure to have her join us tonight. Thank you.
So thank you very much for this nice introduction. So today I'm going to tell you about the properties and the challenges, the new frontiers in studying our Milky Way and the other galaxies which are in the local group of galaxies. So I would like to engage you about these topics. So here you see a sketch about our Milky Way. So our Milky Way is a disk galaxy. It has a disk. This is the galactic plane and belongs to the local group. So there's another galaxy which is called Andromeda, which is the closest galaxy, the bigger closest galaxy in the local group to the Milky Way. So the other twin galaxy of the local group. And it looks like, again, like a disk of stars and gas, a little bit larger than the Milky Way, with a bulge of stars in the inner part. Also, the Milky Way has a little bulge in the inner part. So these are the biggest galaxies in the local group. Unfortunately, the local group has only two big galaxies, two disk galaxies. And then, so actually, Andromeda is almost 3 million light years away from the center of the Milky Way. But there's a bunch of other galaxies, and you can see here that I just used in this sketch, which are dwarf galaxies. So they are little systems which are orbiting like satellites around the Milky Way and around Andromeda in our local group of galaxies. So the most famous one are the Magellanic Clouds, so the large Magellanic Clouds and the small Magellanic Clouds. This pair of dwarfs have been studied since a long time, really have been seen since a long time, even from the ancient people, because they are visible. They are visible essentially from the southern hemisphere of the Earth, even by eyes. And so they are the most famous pair closer to the Milky Way. But the interesting thing is that they are not the closest dwarfs to the Milky Way. There is another dwarf which has been discovered only in 1994, and it's called Sagittarius. That one is the closest dwarf to the Milky Way. Then there's a bunch of other little dwarfs, which are still around the Milky Way. They are more farther away, but they are still orbiting like satellites around our galaxy. So if you look at also the morphology, I just want to give you an idea how they look like, these dwarfs. So as I said, the Milky Way has an extended disk of stars and gas. It has also a lot of dark matter. I will come back to this topic. And also Andromeda is an extended disk of stars and gas. They are huge galaxies. But the dwarfs have different shapes. So the Magellanic clouds look to be like disky, but very irregular. You see, they don't look like exactly, they're not scaled versions of Andromeda or our Milky Way. Then the majority of the other dwarfs in the local group have a different shape. They are more spheroidal. They are just a bunch of stars that look clumping together, and they are not very compact. They are very shallow. So why they are so interesting? First of all, what do we call as a dwarf galaxy? A dwarf galaxy is a galaxy which has a smaller size compared to the Milky Way or Andromeda galaxy, and has many less, the number of stars is much, much less. So just to give you an idea, in the disk of the Milky Way, there are maybe something like 100 billion of stars. But if you look at these dwarfs, they have just a few millions of stars, and these are the brightest. There are even dwarfs which are even fainter and fainter than people are discovering now, and they have just thousands of stars. So it's a really, really different scales we are talking about. So they are less luminous than the Milky Way, less massive, and much smaller in size. Also, which are the properties of these dwarf galaxies? Why they are so interesting? Why I want to engage you about this topic? Well, first of all, these galaxies seem to be very old. So the stars are very old. They have no gas, the majority of them. I'm not talking about the Magellanic clouds, but I'm talking about the rest of the dwarf spheroids which are around the Milky Way and Andromeda. They have a few stars, very old, and no gas. So they are essentially systems. They are very old. They formed in the early phases of the universe, but they still manage to arrive around the Milky Way today. So the Milky Way, it's probably it's much younger, so it's less old than these systems. And so they are a little bit the elves of the universe, and that's why they are so interesting. Also, as I said, some has more spheroidal shape, some are more disky. The ones who are more disky have a bit more gas, they have more stars, also more star formation actually. And also the other interesting thing is that these systems are extremely interesting because they have a huge amount of dark matter as compared to the amount of stars that they contain. So they have a few stars, but a lot of dark matter, and I will get back to this topic again. Also, very recently has been discovered another class of dwarfs, which have been called ultra-faint dwarf. So these dwarfs, you can see, actually, maybe you cannot see here. So they are very hard to be discovered, and they have been only discovered in the last few years because of the abilities, the capabilities of the new telescopes to go deeper and deeper around the sky. And so it was possible to reveal and to see stars which are overabundant or a little bit like overdensities, more concentrated that are inside these dwarfs. Otherwise, years ago, it was impossible to distinguish the dwarfs, the stars that belong to these dwarfs, from the background. And indeed, it's very hard to find them. So why do cosmologists care about dwarf galaxies? So I'm a cosmologist, so I'm interested in understanding the nature, the evolution of the universe, how the matter and how the galaxies are forming in our universe. So we do care because, as I said, these systems form very early in the phases of the universe. They're very old. So if we can understand how they managed to survive up to now, we have extraordinary information about the early universe. So we can know something about the formation of the first systems. And also because cosmologists are, we believe that the most favored scenario for the formation, for the evolution of the universe, is a scenario in which the distribution of the total mass of the universe is essentially dominated from, not from the visible mass, not from the ordinary mass, not from gas, not from stars, not from the atoms we have been formed from, but it's essentially dominated from dark matter. So we don't know exactly the nature of the dark matter, but this is what most of the universe is done from. And we know that we call it dark matter because it does not emit light, so we cannot really see any emission from this matter in the universe. But we know that we interact in the sense that we know the presence of the dark matter because of the gravity. And so in the last 15 years or 20 years, it was possible, thanks to the abilities and the new computational power, it was possible to follow the evolution of the dark matter, so the distribution of the dark matter and the evolution of the universe in the universe using numerical simulations. So this was very helpful to cosmologists. And indeed, this is an example of a simulation I will show you soon, where you could see that we believe in our most favorite scenario for the formation of the universe, or the matter in the universe, that the dark matter was initially a smooth field, so the distribution of the matter was very smooth. But because there are always areas in the universe where you could start seeing, even in the early phases of the universe, that there are areas where there is a little bit more matter than other parts of the universe. Because there are little concentrations of matter higher compared to other areas, the gravity acts, becomes stronger, and so the gravity pulls the matter farther and farther, so it pulls essentially the matter in a way that they form little clumps. And so because these clumps are heavier than the surrounding material, they attract more dark matter, and so they become larger and larger. And so these little clumps of dark matter merge. Initially they are very small, but then the gravity becomes stronger because they are heavier. They pull together material, and so they become larger and larger. And we believe that this hierarchical formation of the matter, the distribution of the matter in the universe, is the way that even the Milky Way has been formed. So you can see here that there are a lot of lumps in the early phases. They come together, they merge, and this is essentially a simulation that reproduces an area of the universe, a volume of the universe, which is roughly the volume similar where the local group, where our Milky Way and Andromeda have been formed. So you could see that we are predicting a lot of little lumps. These are lumps of dark matter. And these lumps, essentially, they merge and they assemble larger halos, are exactly these clumps that we call dark halos. They will host the visible galaxies. So the dark halos are like halos of dark matter around each galaxy, and even these little halos here, these subhalos, will contain dwarf galaxies. So this is the idea behind the formation of galaxies in the current scenario for the structure formation. So why do cosmologists care about dwarfs? Because when we try to simulate, when we see these simulations, you have seen a lot of clumps which come into the Milky Way halo. But these clumps, they should contain a lot of dwarfs. But when we see around how many dwarfs, when people look at, actually 15 years ago, we look at how many dwarfs are visible around the Milky Way, they found that there was a discrepancy in comparison with the theory, with the predictions of the theory. So this was called the missing satellite problem. Now also, so we care because we care about how the Milky Way formed. Also, they are, as I said, these systems are extremely dark matter dominated. So if you compare the amount of stars compared to the total mass in these little systems, they have much more dark matter content compared to the amount of stars than the Milky Way. So why these systems are so small, so old, and so dark matter dominated? This is also a very interesting question for cosmologists. Also, what has been found recently in the last few years, and this is why this topic is so interesting now, is that thanks again to the capabilities of new telescopes to see around the Milky Way and going deeper and deeper and resolving more and more stars, researchers have found that there are a lot of streams of stars and gas around the Milky Way and around Andromeda. And these streams of gas and stars are usually associated, are very spatially associated to dwarf galaxies. And so we believe that dwarf galaxies might be responsible for the formation of the streams of stars and gas. Also because there are so many clumps, visible or not, or maybe completely dark, which are orbiting around the Milky Way and Andromeda. And because the disk of the Milky Way and the disk of Andromeda, they show features like spiral arms, we believe it's possible that there's a connection, there's a link between the interactions of the dwarf galaxies and the disk of the spiral, of the larger galaxies. And so maybe these dwarfs might be responsible in triggering some perturbation and maybe forming some of the features like the spiral arms that we see in spiral galaxies. So the spiral arm formation is a very old problem and usually was essentially studied from mathematicians in previous centuries, and now it's also a matter for astronomers. So what is the missing satellite problem? As I showed you before, this is an example of a cosmological simulation, like the ones I showed you before. So this is the halo that contains the Milky Way. This maybe is the halo that contains Andromeda. And you see these lumps around, which are the subhalos that should contain the dwarfs. So if you calculate the cumulative number, if you sum up all the numbers of these lumps within a certain radius, you see that you are predicting something like 500 dwarfs. We should see 500 dwarfs around the Milky Way and Andromeda in our local group. Now, until I would say more than almost 10 years ago, maximum 15 years ago, the number of visible dwarfs around the Milky Way was only 11. And another 11 were around Andromeda. So it was a really little amount. So there was a huge discrepancy when people compared for the first time numerical simulations with the amount of dwarfs observed around the Milky Way. But I have to say that this question, this missing satellite problem, triggered, it just engaged a lot of researchers to look for dwarfs around the Milky Way. And with the new telescopes, people found more and more dwarfs, fainter and fainter, ultra-faint dwarfs with just a few thousand of stars. And now the number of observed dwarfs around the Milky Way and Andromeda increased a lot. So we are reducing a lot the discrepancy between the predictions and the observations. Of course, there's a huge limit in these simulations. These simulations do not contain any, they cannot describe the visible matter, so they cannot describe the gas and the stars, because it's a very hard job, but I will show you that we are getting to that point. And so they are limited in the sense that they can only describe by gravity the evolution and the distribution of the dark matter. So those spheroidals are also interesting, as I said, because they are most dark matter-dominated systems. So this is, again, an example. So this is one of the dwarf spheroidal around the Milky Way. So you can see that it's a bunch of stars, very, very, very shallow. And this is another dwarf, so it's very hard to find it, because it's difficult to distinguish the stars that belongs to the dwarf from the background. This is why, essentially, this problem, the search for dwarfs around the Milky Way, is so difficult. So if we want to, as cosmologists, if we want to understand how this system formed, we need to come up with ideas, with processes that can remove stars and gas from the systems like dwarfs, because they need to remain dark matter dominated, because that's what the observations essentially showed us. Indeed, when researchers measure dwarf spheroids, they know that they have a lot of dark matter because they can measure the motions of the stars inside these dwarf spheroids. And the motion is pointing out that there's much more mass. The motion of the stars is like if the stars act, if there's much more mass than what we really observe. And so that's why we believe that there's a lot of dark matter in these systems. So the classic theory to explain why these systems are so dark matter dominated is to go back, to point out, or simply to appeal to an epoch in the phases of the universe, in the evolution of the universe, which is called the reionization epoch. It's a period where the gas around the universe was warmed up from the light, from source light, essentially. And so it was warmed up, and if you have the gas in little subhalos, they should contain the dwarfs, and the gas should form the stars when collapses inside these little halos. So this theory says that maybe because it's warmed up, the gas will evaporate from the dwarf and so will not form stars. And that would explain why these systems don't have many stars and they don't have gas. Of course, to prove this theory, it's very hard. It's very difficult because simulations where the ionization can be included in a good way at this time are not available yet. So we can only make hypotheses, but we cannot really test this theory. So because of this, we came out with another idea. So a couple of years ago at Harvard, we published this paper where we proposed that maybe dwarf spheroidal galaxies, they become so dark matter dominated because of process that can remove efficiently stars and gas, but not the dark matter from the dwarfs. And I will tell you in which way. So our idea was that initially, we know that in the early phases of the universe, the dwarf galaxies should be the dominated population of galaxies because the little things form first in our scenario for the structure formation. So because of the gravity, if you have two dwarfs, and initially we know that the dwarfs probably in the early phases of the universe were more disky, or the galaxies have been more disky initially. They are not spheroids, but they have this component. By gravity, the dwarf can attract one another, and so if they have a similar mass, they can merge. But if they don't have a similar mass, they just interact one another, so they orbit one around the other. So this is a simulations that we have done where we simulate two dwarfs which are approaching one each other. They are just interacting. And so you can see after a little short time, you start forming a long stream of stars. And this is one of the dwarfs. This is the little dwarf, which is the victim. It's losing a lot of stars. And after a few other time, you see that there are some features which are formed like shells of stars around the larger dwarf. So what happens here? Why do we lose stars and we end up with something which is dark matter dominated? So we believe that what happens in these simulations is that there's a sort of gravitational resonance. Now, resonance is sometimes a difficult task to be understood. Just to give you an idea what the resonance is, usually we have, so if you heard about this, but there was this bridge, it's called the Tacoma Narrow Bridge, and they built it up, I think it was in 1940. You could see that there are vibrations in the bridge. Essentially, also at the end of the movie, the bridge collapses. So these vibrations are driven from the wind. So what happens is that the wind perturbs the bridge because it drives it to its natural frequencies. So when the frequencies matches, you have a resonance. You have a sort of when they match, essentially, that's how the resonance works. So in our case, we have a little dwarf which is the victim here, that feels the perturbation from a larger perturber. So the other dwarf is like the wind. It's driving the stars which are rotating in the disk to their natural frequencies, to the natural frequencies of the victim. And because of this match in frequencies, you start losing material. And I will show you how. So we are talking about a process which is called gravitational, we called it gravitational stripping, resonance stripping, or gravitational resonance. So the interesting outcome, the surprising outcome of this process is that if you try to quantify how much dark matter a system has, like a dwarf, when it's going through a resonance, a gravitational resonance. So initially, we have a fixed amount of stars compared to dark matter, but when the dwarf interacts with the other dwarf and it's in resonance with the other dwarf, with the orbital, when it's a spin frequency, it's in resonance with the orbital frequency, you start losing material, you start losing stars, And so the amount of dark matter compared to the amount of stars, it's increasing. And that's a way we try to explain why these systems are so dark matter dominated. So in the simulations I showed you before, these are the same simulations. In this case, we really we paid attention to have the resonance happening. And this is the little dwarf, the victim, which is losing material at the minimum distance from the larger system, which is the perturber. You see, you form this stream of stars. So the outcome of this process is the formation of tails of stars. We made the same simulation, but in this case, we paid attention not to have a matching frequencies, so not to have a resonance. So we did not align dwarfs in a way that they had a resonance. And indeed, you don't see the very extended tails that you see in this case. So what I want to show you essentially is that this process might be interesting because in certain conditions, when the resonance happens, it's very efficient in removing stars and gas. So how do we form these tails of stars? So how it works? So if you are in the case where the resonance happens, so you should look at now this sequence counterclockwise. So here I sketched the little dwarf. This is the victim. So these are the stars rotating in the disk. And they are feeling the perturbation from a larger dwarf. So in this case, because we set up in a way that the disk is rotating and it's aligned, it's rotating in the same direction as the other dwarf is coming along the orbit, and because we want to have a resonance in this case. So if you focus on a star, the star will feel the perturbation, will feel the gravity from the perturber, and you see that it's rotating. So after a short time, it's just rotating here in the disk. But the perturber also is going on the same direction. So they are going both on the same direction, so the stars are always pulled in the same direction because the perturbers is always aligned with the dwarf. And so because of this resonance, they will pulled always in the same direction, and after some time, the stars will start going far away from the dwarf, and so you start forming like a long tail of stars. But in the case where the resonance doesn't happen, and this is a case where the stars are rotating in this direction, and the perturber maybe is rotating on the opposite direction. So in this case, they are not aligned, so the frequencies do not match. And so if you look at this time clockwise, the sequence, so the stars rotating this way, so after a while is here, but the perturber is on the opposite side. And so the stars are pulled inwards, outwards, inwards, outwards. That means that at the end of the sequence, they are not so far away from the dwarf, they're just stuck very close to the dwarf, and so you don't form any tails. So maybe you can believe that this process might not be common because it's about resonances, how often they match these frequencies. Indeed, it is very common. It was already discovered from tumor. Actually, it was pointed out from tumor a long time ago from a scientist that worked for a long time at MIT. And let me show you. This is a simulation of two these galaxies interacting by gravity. And these are images that you can see on the sky. So this is an image of interacting galaxies in the sky. So these are real observations. These are called the antennae galaxies. They are two galaxies which are merging, in the process of merging here. And you see here, even here and here, long tails of stars. And if you see in a simulation of interacting galaxies, that we form also stars, long tails of stars, very similar to what you can observe in the sky. So this process is very common. You see here, this is very similar to the antennae galaxy. You see here when they are almost merging, and you see these long tails of stars, which are due to this gravitational resonance, this resonance stripping. Also, it's interesting, if you look at the sky, there are other galaxies like the famous tadpole galaxy. So this galaxy has a long tail of stars, and it's interesting because it has in reality, it's an interaction of two galaxies. You see the bigger galaxy here, the little galaxy is here, So it's almost inside the other galaxy. And the tail belongs to the little victim. So it does not belong to the larger galaxy. And this is a simulation we have performed where the resonance is happening. And you can see that we can also get similar features. Also, this is a simulation we have done, and these are observations. So this is, again, a simulation of two interacting dwarfs. And you see shells around the larger dwarf. This is the little victim, which has been stripped of stars. And you see here in images of this galaxy, the NGC 2782, it's also an interaction, and it looks like there are a lot of shells around the stars. So these are not the only signs of resonances or stripping or tidal interactions around the Milky Way. There's a majestic Magellanic stream of gas. It's called the Magellanic stream because it's associated to the Magellanic clouds. It's a huge stream of gas. You can see here, so this is the plane of our Milky Way, the galactic plane. So this huge stream is a huge stream of gas. So it's observed in radio. And you can see that it goes along the sky. And these are the two molecular clouds. So the giant and the small, and the large Magellanic clouds and the small Magellanic clouds. So this is the pair of dwarfs, and this gas is associated to them. So probably it's lost from the Magellanic clouds into the Milky Way. So the origin of this majestic Magellanic stream was unknown for a long time. Was very puzzled. And so there are two ideas behind how this stream can be formed into the Milky Way. So one idea was that this gas is stripped from the clouds when they fell into the Milky Way. And there was also, for a long time, it was also, people supposed that the Magellanic clouds were orbiting along the Milky Way since a long time, for many, many orbits. But very recently it has been discovered that the Magellanic clouds, thanks to new measurements of their velocities, it has been discovered that they are just falling into the Milky Way for the first time. So these pairs of dwarfs are just coming into the Milky Way very recently. And so this made the puzzle a little bit more complicated, because the other idea was that these clouds might interact by tidal interactions, so by sort of resonances, and they might produce, might lose some of the gas from their disk, and because of the interaction of the two dwarfs, and then this huge stream of gas is just amplified by the gravity, by the presence of the Milky Way once they fell in. And indeed, in the last few years, a few years ago appeared this radio image of the Magellanic stream. So the observers found that there are essentially two tails. There's a trailing arm and there's a leading arm. And so usually, and these are the two clouds. So, and you can even see a bridge of gas between one cloud and the other cloud. So the idea is that it's probably, these observations are essentially supporting the idea that the Magellanic stream has really an origin, a tidal origin. So it's really due to the gravity between the two clouds. And also because we see some gas that's attracted from one cloud to the other cloud. So it probably came together as a pair. And when they fell in, also they were losing already the gas, but when they fell in, this gas is amplified. And indeed, I think Gurtina Besla made a very good job in showing last year that this is a model where the pairs of dwarfs, so the two clouds, are losing by tidal interaction their gas, and once it falls into the Milky Way, it's essentially amplified by the presence of the potential of the Milky Way. So again, you can see the same model. So now the clouds are interacting by tidal interaction, so by sort of gravitational resonance. And as an outcome of this resonance, there is this stripping of the gas. And then the gas goes across the sky exactly, very similar, in a very similar way as essentially this is how they look like now, where they are positioning now, the two clouds. But the majestic Magellanic stream is not the only stream we have in the local group. I think thanks to the PANDA surveys, so this was a new survey that came out that's essentially finishing the observations just now, has found that this is a Canadian Hawaii telescope survey. So they found an amazing stellar halo around Andromeda. So this is Andromeda, the twin companion of the Milky Way. There's a huge stellar halo around Andromeda. And for the first time, this survey could really resolve the details of, really of these stellar halos. So it found a lot of little dwarfs, and associated to these dwarfs, which are these spots here, there are a lot of little streams, which are the result of, again, tidal interactions of the dwarf with a larger system like Andromeda. Also here, there's a companion, a dwarf galaxy companion of Andromeda. It's called the M33. And also, I will show you that the interactions between these two galaxies, it's probably responsible for the formation of the huge stellar halo. So this halo is extended almost something like 900,000 light years. So here around M33, it's already, this circle here, it's around 300,000 light years. And there are also distortions due to this tidal interaction. They are probably exactly due to the fact that the two galaxies are essentially interacting by gravity. So in this simulation, Jan Dubinsky has shown what probably happened in Andromeda in interaction with M33, and that's probably how the result of this halo came out. So initially, M33 was probably a certain distance from Andromeda. So now it's interacting. So you see these tails of stars. They are due to these tidal interactions. So they are, again, a sort of gravitational resonance happening. And then this is the maximal distance where M33 is from Andromeda. And now it's coming.
So it's going a straight line back and forth, not over there. It's not
No, there's also an orbit, and now it's, yeah, there is. So the interesting thing is that it's losing a lot of material, M33, and you see that the stars are forming streams, and then they are pulled back towards Andromeda because they are attracted by gravity. So this kind of simulations, and they can justify, also they can support our idea of the hierarchical formation of galaxies, because they show that essentially the dwarf can lose material, can lose stars, and these stars goes on the larger halo of the largest galaxy. And so all the little stripping that we see here, all the stars that we see here are probably just lost by stripping when these dwarfs are orbiting around the larger galaxy. And so this hierarchical structure formation scenario is probably correct. Also, if you see, M33 has also disk. This is a disk of gas, and there's a little bridge here of gas. The gas is distorted. Also, these distortions are due to the interactions with Andromeda. So even if the dwarf don't really pass through the galaxy, but they are just interacting by tidal interactions, they can still be distorted and losing material. Also, another interesting topic for cosmologists, and why do we care about dwarfs, is that, as I said, we are predicting a huge number of clumps which should orbit around the Milky Way. We don't see all of them, but they might be also interesting because some of these clumps might pass through the disk. They just beat the disk, and they can excite the disk in a way that the disk reacts, forming maybe the spiral arms that we see around the Milky Way. Well, we don't really see it around the Milky Way, but we see around other spiral galaxies, and we believe that also Milky Way has some spiral. This is a simulations we have performed at Harvard about the formation of spiral arms. So here what we did is to consider a galaxy. So we set up a galaxy with a huge number of stars. It's not really matching the Milky Way, but it's still 100 millions of stars. And then we bombard the disk with these dark clumps as they are predicted from cosmology, as they are predicted from our theory of structure formation. And we see what happens if we can really excite the disk and form in this.
What?
Excuse me?
Bombarded it with what?
With clumps, with dark clumps, with dark clumps. We are bombarding the disk with dark clumps, and we see if these clumps or these dwarf galaxies passing through the disk can perturb the disk in a way that the disk reacts and form maybe the spiral arms that we see in spiral galaxies. So the answer is essentially we do not believe much about this scenario, so they're probably not responsible for the formation of the arms, because if you see the shape of these arms here, they look like circles. So they are much more round than the one that we observe in the spiral galaxy in the nearby. So in this case, the arms, what we observe are like segments, and so they are more open. And in the case where we bombard the disk with, we consider the clumps as the source of this perturbation, we see shapes which are not exactly matching what we observe. So indeed what we are doing now is, since if you look at the sky, the shape of the arms is very different. So our galaxy, the Milky Way, maybe looks like this galaxy here. So this galaxy, for example, is not interacting with any visible dwarf. It doesn't have any visible dwarf very close. But there are other galaxies like M51 that has a lower number of arms, only 2 maybe. And in this galaxy, there is a satellite galaxy which is interacting with this galaxy here. So maybe in this case, it's possible that the tidal interaction are the source of perturbation that excite the formation of these spiral arms. But maybe for this kind of galaxy, it's more hard to say. So what we are doing to try to simulate this kind of galaxies where there's no obvious interaction with the visible dwarf is to consider clumps of gas which are co-rotating within the disk, and we are finding that this kind of idea is supporting, actually is reproducing some of the observations. So this is one of the outcome of our simulation. So this is the disk of a galaxy simulated, inclined. Here it's face on. So you see that we start forming arms very quickly. And they look like that they are also long-lived. So you see that they are much more open and more like segments, more in agreement with the observations for many of the spirals. Also, I will end my talk giving you an idea about the final frontier for galaxy formation. So I told you before that we tried in the last 15 years, 20 years, people got a sense of what's going on in the distribution of the dark matter in the universe by gravity. So using numerical simulations, we are able to understand how the halos that host the visible galaxies are built up. So even the halos of the Milky Way, the halos of Andromeda, our local group or groups of galaxies. But we were not able to introduce in a correct way the hydrodynamics, so descriptions of the physics like how gas and stars evolve in the universe in a self-consistent way, in a cosmological context. But finally, I think this is a new time. It's a good time for doing theoretical astrophysics, because it's also cosmology, because there are now new codes which have been developed recently that are able to describe more correctly the physics of the gas and the stars inside the galaxies, and to follow maybe in a proper way, in a self-consistent way, the formation of galaxies like our Milky Way. So this is an example of one of these new simulations that are coming up. So it's a cosmological simulation, so it's not dark matter only. There's also gas and stars inside. And so you can see this is a volume of the universe simulated And we can start seeing with a very unprecedented detail what's coming out and how the galaxies are formed. So here we are zooming on galaxies. So this galaxy might look like the Milky Way. So you can see this is an extended disk of gas. Around there's all dark matter and gas along filaments. So you can see that looks like a disk. There are even spiral arms now appearing here. So the other clumps that you see around are very far away, but these are other galaxies that are forming in this volume of the universe. And also you could see here tails. So here you see interacting galaxies. So these are two disk galaxies that are interacting, and these are tails of gas and stars that will come out as an outcome of these tidal interactions. So we are finally achieving the point in the time where we can study properly galaxy formation, and eventually we can compare to the observations. So also from the same kind of simulations, so this is a sample of galaxies like the Milky Way. Some look like the Milky Way, some look like more spheroidals, some have features here like tails or rings. So there's a sample of galaxies that come out in a self-consistent way in a cosmological context that might look like what we observe in the sky. So I think it's a good time to do theoretical astrophysics because we have due capabilities in telescopes to find more and more dwarfs, to look at more in details how the Milky Way look like, how the stars are monitored around the Milky Way, and also we have all the theoretical tools to study in details how they form in our universe. Thanks for your attention.
Do you have to write the simulation software yourself, or are there packages into which you can put your data? And second, when
Yes.
you first showed the rotation.
So you first asked about the code, which code we use. So we don't, usually we don't develop codes because these are very difficult simulations. So there are codes that have been developed along the years, and in particular at the Max Planck, this code is a new code that will not be available to community, but is available to our group. And so these new simulations have been done thanks to the capability of this code to describe better the physics. So we use a very complex code to describe aerodynamics and the dark matter distribution. And the second question was so if we pick up a particular time when we look at, so we usually, in these cosmological simulations, we usually follow the dark matter distribution and eventually now the gas and the stars for 13 billion years. And so up to the time that we observe today, and we want to compare what comes out from the simulations what we observe in the sky today. But of course, the fact that we can use simulations help us because we can stop or we can have a snapshot of the simulations along the time. And there are observations of high redshift galaxies, so galaxies which are very far away. That means they are very back in time. And so we can still compare, along the time where we run the simulation, what's going on in the evolution of the galaxies. So this is one of the big goals that we try to achieve in doing numerical simulations like this. They are a wonderful lab to compare the data along the time with what we predict.
When you say dark matter has a halo, do you mean a dark halo or a halo of light?
But we say dark halo, so she's asking about what I mean with dark halo. So this is a halo that's surrounding each galaxy. So it contains the visible galaxy, and it's done of dark matter. Maybe. Yes.
Yes. You're looking at some of those gas spirals. They look strikingly like a hurricane. Is there any similarities to be drawn between the behavior of clouds on Earth and gases in the galaxy? And can observing one form facts about the other?
Well, the features maybe we were talking about, it's that are these arms that are very, very strong. They are like arms that are formed inside the galaxies. So the formation of the arms is still very debated. I think it's, I said before during my talk, this was a problem that was approached already from mathematicians in the previous centuries. Now astronomers are trying to explain it. So it's not really exactly clear what drives the formation of the arms. But it's, so the idea is that probably the most common idea is coming out now is that it's a sort of reaction of the disk to some perturbation. So it's something like a perturbation that's driving a reaction of the disk, a dynamical reaction. And so because of this reaction to the perturbation, the disk starts forming wakelets, which becomes like the arms that we see around. So it's not vortexes. So it's not in that case, it's not a similar thing like vortexes. But it's really driven from the gravity inside the disk. Maybe?
Yes, we talk about looking back in time millions and millions of light years away and seeing the earlier formations of the universe. And other matter that we're looking back at.
Yes, maybe it's a sketch here. So initially there was a Big Bang.
Yes.
Then very quickly, the material, so the universe evolves in a few minutes, essentially. So all these simulations are essentially in agreement with the Big Bang theory because they are based also on the cosmic Milky Way background, so the background radiation that has been only 380,000 years after the Big Bang. And so the evolution of the universe comes in a way that the structural formations happens much later. But even before, you start having the seeds of the structural formation. Because of the gravity, you start forming first these little halos by gravity. They collapse, they form clumps, and then they will host the future visible matter. So what we were able to do until a few years ago was only to follow in a correct way how the gravity works. But now the gas and the stars also can be added to this picture. It's just that the hydrodynamics is very complicated, and so it's difficult to know if we can end up with a picture that looks like exactly what we observe. But these codes and now this new frontier in cosmology will probably be able to tell us if there are discrepancies or not between the theory and the observations. For example, I talked about missing satellite question. So where are these dwarfs that we don't see? But it's also true that we never introduced in a correct way before this time now the baryons, so the visible matter like gas and stars. And so maybe new simulations that are coming out now at this time can reduce still the discrepancy between the observations and the theory because we properly follow also the visible matter. Maybe on the back?
I think that gentleman was asking actually how the matter got dispersed to such a great distance between the galaxies. Because the stars are all moving at different speeds.
So how they get the spin, the galaxies? Are you asking this?
Yes, that's my question.
Yes. So they get spin because you have because initially you form these, you form filaments in the early phases of the universe. So you form, so initially when you look at these simulations, you start forming large scale structures. And these filaments, by gravity, by torques, so they exert some gravity, some interactions on the clumps, which are the host. They will be the host of the visible galaxies. So these clumps start feeling this gravity, and they start spinning.
But how is the angular?
So initially, okay, in these simulations. So the gas collapse, it collapses. You keep the angular momentum conserved. So the gas collapses in a disk, and so you start having. So you conserve the angular momentum essentially, and so when you go to the very small scales, that's still unclear how the cooling happens. So we don't know if it's how the spin really will work on the very little systems. But in these systems, you just have conservation of the angular momentum, and so the gas collapse and start going on a disk. And the disk, and essentially the spin, is gained from the torques that they feel from the large scale structure. So that's the way they get up the spin. So the details exactly are not known yet, because these simulations are just the first attempt. So we have to look at exactly if things work as was supposed that they should work. So in the previous years, essentially what was failing with these kind of simulations was that so the previous codes were not able to form consistent disks. So the visible matter, so the gas, was really collapsing in the inner parts of the disk. It was not really conserving the angular momentum, and so for that reason, you were not ending up with nice disks, but only with like a bunch of gas in the inner parts of the galaxy. And so it was not possible to see how disks also can interact and can merge and forming different kind of galaxies that we observe in the universe. So this is probably the first time we can do something on that way. Maybe that?
So is dark matter energy and dark matter?
No, we assume, okay, in the kind of simulations we have done, we are assuming that because we know that we don't know what is the dark matter, but we know that dark matter is almost 90% of the mass of the universe. And so we are assuming that there's a halo around each dwarf, and the halo is distributed as the cosmological simulations or the theory tells us should be distributed. So it's not very concentrated in the inner parts. So essentially it's not very, it's a halo in the outer part of the galaxy. So in the inner parts of a galaxy, even of a dwarf, the dominant part is always a little bit of baryonic ordinary matter. So we simulate assuming that the dark matter is what we suppose it is from theory. So we cannot really prove that it's, with this kind of simulations, this idea, which kind of dark matter is, or if it's a correct scenario. We just try to see if we end up with a scenario with the process that can explain why the dark matter is so dominating in these little systems.
But does the dark matter feed the creation?
The dark matter is not removed because it has different orbits. So because in the simulations we see, if we believe that dark matter is cold dark matter, as this theory is supporting, is predicting, so it's the orbits of the dark matter by gravity are very different from the stars in a disk. So it's not rotating in a disk. It's just it has just random orbits, all the particles of dark matter. And so if this is true, that means that they cannot, maybe some particles of dark matter can resonate, can feel, of course, this resonance stripping, but globally, since there's no rotation of the dark matter, there's no consistent rotation of the dark matter globally, because the orbits are just random, and so you cannot globally remove the dark matter like you would remove the stars or the gas by this process. So it's just because of the different nature, because the dark matter does not rotate, that you don't have this coherent resonance for all the dark matter. Maybe on individual particles, yes, but globally not, like if you have a rotating disk. So that's the idea. Of course, if you don't have a rotating disk in first principle, then you cannot remove, this idea would not help, would not work.